Good evening, students.
Good evening, sir.
We'll get started. So what was the last topic we saw in the previous class?
Sir, it was solenoids and toroids.
Okay. I told we'll do a problem, right, based on Ampere circuit. So I hope you're able to see my screen. Yes. So yesterday, what is Ampere circuit, right? What is it? The line integral of B dot dl, right? The line integral of B dot dl is equal to how much, guys? Mu naught times the current enclosed by the Amperian rule. I hope you remember this, right? Now the thing is, we'll apply it in this problem. Mark it as important. Okay. Let's see how to solve this. So figure 4.15 shows a long straight wire of cross-sectional area of cross-section with radius A carrying a steady state current I, and the current I is uniformly distributed across this cross-section. Calculate the magnetic field in the region R less than A and R greater than A. Okay. So did you understand the question? So here in this figure, there is a long. What do you mean by long? Long means infinite length. So you have a long straight wire of circular cross section of radius A, and it is carrying a steady state current I. And noted here is the current I is uniform. I is uniformly distributed over the cross section. Anybody? If suppose I say the current is distributed over length, what do you mean by that? Think about it. If I use a statement like the current is distributed over length, what do you mean by that? Then the amount of current that you're trying to talk about will be a function of L. Right? Are you guys able to understand this? So the current is distributed over the cross section means, let me explain it by showing. I'll show you something. Listen. See, listen. If I take this pen as the current carrying conductor, so if you read the question carefully, what did they say? They told that the current in this wire is distributed over the area. So what is the cross-sectional radius they have given us? So what is the radius of the circular portion? Anybody? The question clearly says cross-section in the bracket they have given radius. So what is the radius? It is A. Is that clear? Now, what is going to be the area of this cross-section? Guys, what is so tough to answer? I asked a very basic question. If the radius of the circular portion is A, then what is going to be the area? Why is no one speaking? Am I audible or not in the first place?
Sir, you are audible, sir.
Then speak. No.
So is it
What
2A?
A, 2A is the diameter. I asked what is the cross section? area. It's a basic question. It's what are you able to see this side? For a cylinder, what does the cross section represent?
Pi r square. Oh,
It is pi r square. What is the
Pi r
so tough to answer? It is pi a square because the radius of this portion is a. Right. So the cross sectional area is pi a square. Now, if you take this into small concentric circles, then the current is distributed over every concentric circle that you're going to take into consideration. Okay, that is the meaning of the current is distributed over the area. You're able to understand that point. So the current is going to get distributed over every cross-sectional area. Now, then what is going to be the total current? So, if you read the question carefully, the current is distributed over the cross-sectional area. Then we need to calculate the magnetic field in the region where the value of R is less than A and the value of R is greater than A. Means if you take a cylindrical portion like this, okay, wire generally takes the shape of a cylinder, and if this radius is A, then what we need to do is you need to take a small portion inside. You need to take a small portion inside whose radius is R, where R is less than A, and we need to find what is the magnetic field produced due to the current through this cross section first. And R greater than A means you will consider a loop like this. How to solve this? So, what is the value of current we are trying to talk about? So, can I say the total current is distributed over the cross section? So, can I say in area? Wait, I will write it in a separate page. See, if any step is unclear, please ask, okay, or else I will not understand whether you guys are clear or not. So, if I take this portion, okay, then what is going to be the total current through this area, guys? So, total current is I throughout an area of how much value? Pi a square.
Yes.
So, if I take a small portion inside, then can I say that the current through that portion is I dash, and what is going to be the area corresponding to it? It will be pi r square, where r, correct?
R
Now,
is less than. Yes.
okay, you just cross multiply and write it. They will be in the same proportion. So pi and pi will get cancelled. So I dash will be equal to I into r square divided by a square. Let this be equation number 1. Okay. Now I am applying Ampere's circuital law. Okay. When I apply the Ampere's circuital law, I will get the line integral of B vector dot dl vector is equal to mu naught into I net. This we know. So line integral of B is what we need to calculate into dl into cos 0 degrees is equal to mu naught into what is the net current that is flowing through the small portion that you have considered. Is it not I into r square divided by a square? Right. So B is a constant. The line integral of dl will be equal to mu naught a square. Now tell me, with yellow color, see, what does this portion represent? When you add up all the DLs, what does this portion represent? The sum of all the DLs will give you the circumference of that particular circle. So B into 2 pi r will be equal to mu naught into I into r square divided by a square. R and r will get cancelled. So what will be the value of B? It will be mu naught I divided by 2 pi a square multiplied with r. So this is the value of magnetic field for the value of r less than a. Is everyone clear? Is every step clear? See, this is an often asked question. Please make sure that you're clear with every step. So B is equal to okay. Now, shall I proceed to r greater than a? So for r greater than a, line integral of b dot dl will be b vector dot dl vector will be equal to mu naught into I net. But now, where are we considering the loop? You're considering it outside. Okay. So for this outside portion, the line integral of b into dl into cos 0 degrees will be equal to mu naught into, what is the value of I net here, guys? So what is the total current that is enclosed in the conductor? It's very simple. What is the total current through the conductor?
So this is a I1 plus I2.
Of dl will be equal to mu naught into I. So what is the line integral of dl here? It will be 2 pi r is equal to mu naught into I. So B will be equal to mu naught I divided by 2 pi r. Means here it is going to behave as if the cylindrical conductor is going to behave as if it is a circular conductor, and due to a circular conductor, what is the magnetic field at the center? You get the same value. Okay. So if you write it as a function, B will be equal to mu naught I divided by 2 pi a square multiplied with r for r less than a, and B is equal to mu naught I divided by 2 pi r for r greater than a. So when you draw the graph for this, when you draw the graph as a variation of B and r, for a value of r which is less than a on the left of it, you will get a straight line like this. And for a value which is greater Students, was there any issue from my side?
We weren't able to hear you, sir.
From where? From which point?
You were,
Screen is also
you,
not.
you started drawing that graph and everything went off.
Okay, I started drawing it and everything went off. Okay. Now you are able to see.
Yes, sir.
Sir.
Yes. So what I'm trying to say is the value of magnetic field is equal to mu naught I by 2 pi a square in
Now I
R
can't
for-
hear you, sir.
is it the problem for everyone? Are you guys able to hear me or not?
So suddenly your audio just shuts off. Sir. I can't understand.
Is it breaking often?
No, sir, we can't hear you at all. Sometimes.
Okay. Now is it better?
Better, sir.
Yes, sir.
So I'm trying to say for the value of R less than A, the value of magnetic field is directly proportional to R. So you will get a straight line passing through origin. And the value of B, when it is inversely proportional to R for the value of R greater than A. So here you will be getting a rectangular hyperbola like this. You will get a curve. So this is the graph. So that's all with this chapter, and we are done with it. I think we have done the textbook problems also. So is there any doubt, any topic that is not clear from this chapter which you want me to explain again? Is there any topic that you want me to explain again? Guys?
No, sir.
Okay. Then I think we are good to start with the next chapter. Just give me a minute. I'm opening a file. I'll be back. Yes. I think I'm audible, right? So you guys are able to see my screen,
Yes, sir.
right? Yes, sir. So the next chapter that we are going to start, this is a small chapter, okay? So the lengthiest chapter is only the fourth one. All other chapters are small. or reasonably more. So the fifth chapter is magnetism and magnetism. Okay. So in the fourth chapter, what did we learn? We discussed about the moving charges and magnetism. And the fifth chapter, again, we are talking about magnetism. What do you think is the basic difference between them?
I think there we discussed about how electricity produces magnetism. Here, the naturally occurring magnets, I think we'll be discussing.
Okay. That is, you're going to talk about there we spoke about electromagnets, and here we are going to talk about the permanent magnets. Right? So that is the meaning. Next is, if that is going to be the scenario, then we need to understand one point. We know all these things, right? Magnet is a material which can produce a magnetic field. So magnetic field is invisible. However, it is mainly responsible for the most notable property of magnet. What does it do? According to magnetic property, the magnet will try to pull all other objects, the magnetic materials, towards itself, right? So around the magnet, there is an invisible region which we call it as magnetic field. All these things we have discussed and we have calculated in the previous chapter itself. But the important question that arises here is, what was the last chapter mainly speaking about? The last chapter mainly spoke about one important point. What is it? That is, for you to generate magnetism, what is necessary? When can you observe the property of magnetism being exhibited? When can you produce it? That was the objective of the whole
Poles. Two poles. Two poles. Polarity. Okay.
Two poles will get generated.
Okay.
Okay, magnetism means when you talk about a magnetic material will have two poles, no doubt in that. But the question is, where is that polarity getting generated from? That is what we need to answer.
Charges are
So
moving.
Sorry?
When the charges are moving.
Very good. So the last chapter clearly told us one important point, that for you to generate magnetism, what is needed? For you to generate magnetism, you need
Movement of charges.
You need the motion of charges. You need to put the charges into a particular motion. That's what the concept told. Right. The next question is, in the previous chapter, again, see, the next important question is, when you talk about a charge, what are all the factors that come to our mind? The first two chapters told when the charge was at rest, there used to be a region around those charges, which is called as electric field. Right. Secondly, we understood if the same charges are put in motion, then there is a region around the substance which we call it as magnetic field. Correct, Ada? So, when the charges are in motion, especially in an aligned motion, can I say that current is constituted rather than ambiguously saying that the charges are supposed to be in motion? Can I put a statement like this? The charges need to be in aligned motion, means they should contribute to the electric current so that you are able to generate magnetic field around that particular material. Accepted? Now I have another question. When you talk about a permanent magnet, how do you think is that material able to exhibit the property of magnetism always? That is the reason why we call it as a permanent magnet. I take a bar magnet, I take it close to any iron material, you can easily sense the material being pulled towards it. Right? But how is it able to exhibit? Because you take a bar magnet, are you taking that bar magnet and connecting it across any battery? Do we do that?
No, sir.
Obviously, we don't do it. Right? Obviously, we don't do it. Then, when moving charges are the responsible factor for generating magnetism, the permanent magnets, where are they getting the energy from to exhibit the property of magnetism? That is the first question we need to answer. Can someone guess what exactly is happening? Can someone guess? It has something to do with the atomic structure.
What is it? That ferromagnetism and stuff.
Need not be ferromagnetism. There are other magnetic materials also, paramagnetic, diamagnetic, ferromagnetic, antiferro, all those things are there. It has nothing to do with ferromagnetism. In general, I'm trying to say, I'll put a statement like this, you'll not be able to believe. Every material in this world has magnetism. Every material property. The only thing is,
Sir, I can't hear you.
Sir, you are not audible, sir. Didn't hear you.
guys, sorry, there was some issue. So, okay, I would like to ask the question again. What was the last point that you could hear?
Every object.
Every material in this world exhibits magnetism, but the extent to which the magnetism is exhibited by a material will change from one to another. How am I able to pass such a statement? It's because, see, I'll ask you some basic question. This mobile is there, right? I have a mobile in there. I hold it like this. It is able to stay at this particular position because there are some balance forces, all those things acting, right? But if I keep the mobile on the table, why is it not able to on its own? Because it has some intrinsic property associated with it according to Newton. What is it?
Inertia.
It has a property of inertia, right? And why is inertia coming? Because the substance is having mass. So any substance in this world which has mass will possess a characteristic, an intrinsic property, a naturally occurred property within itself, which we call it as inertia. In a similar way, if I talk about, I take this mobile phone, I rub it against some surface and try to take closer to some other, I try to take it close to some other object, then you can see that it exhibits a property of attraction or repulsion. Depends on what the other object is, right? So what happened to it? I created
It is
friction.
charged.
I charged it, right? When I charge the material, what do I mean by charging a material?
It gains or loses electrons.
I'm talking about gaining or losing of an electron. So wherever there is a process like this, wherever there is a gain or loss of electrons taking place, the material is able to acquire a property of getting charged, right? So when it is getting charged, listen to this carefully. So when it is getting charged, can I say that material is
Sir, I can't hear you.
again,
Yes, sir.
Now I can hear you.
It got stuck, sir.
Now again your video.
Now
I guess it should be better now. Let's see. If there is an issue again, please let me know. Okay. Is it better now?
yes, sir,
Yes,
you're
sir.
audible.
Okay, that's enough. What was I saying? Yes. Wherever you see charge, the intrinsic property of a charge is to generate electric field around it. Right? I'm actually giving you hints, guys. I want you to think. I'm trying to make you think. Now comes an important question. When I say every material has magnetic field around it, like you will have, I will have, everybody will, right? But we cannot exhibit that amount of magnetism. There is a reason for it. That story we will see it. What exactly is happening mathematically? I am saying every material is going to have magnetism. How?
Because all the material has charges, right?
Yes, that is important. More importantly, it is not because of charges. Those charges are in motion according to the atomic structure. So when you take an atom, basically, an atom comprises of what?
Protons, electrons, and neutrons.
Protons, electrons, and neutrons. The protons and the neutrons are bound within the nucleus, whereas the electrons are revolving around the nucleus. They're in continuous motion. When the electrons are going to be in motion, can I confidently pass a statement saying that the electrons will constitute to some current? Can I pass that statement? Electrons are there. When the electrons are in motion around the nucleus, one thing that is happening is the electrons are able to move around the nucleus because there is a centripetal force acting, which is provided by the electrostatic force. Apart from this, since there is a motion of electron, the periodic motion of electron is taking place around the nucleus, can I pass a statement saying that these electrons constitute to some electric current? Yes or no?
I think yes.
When that electric current is going to get generated, when the charges are in motion, what is present around it?
Magnetic field.
Magnetic field.
So, from all these things, can we conclude saying that every material is made up of atom and every atom is going to have electrons in motion? Can I confidently say that any material which is made up of atom is going to exhibit magnetic property? Yes or no?
Yes.
Yes.
So that is what we were trying to understand till now. So it is a basic intrinsic property of every material to exhibit the property of magnetism. Now comes an important question. If it is able to exhibit, how much is going to be the value because of the motion of this electron is what we are going to start with. Right? Shall we get started?
Yes, sir.
Yes, sir.
So let's see. Now, I just wanted to show you something. So in the fourth chapter, I would have left one concept alone. If you see, the magnetic dipole moment of a revolving electron. This is the only concept that I would have left. Okay. Because this is the building block for the fifth chapter. Okay. This is actually a part of the fifth chapter. And let's get started. So just whatever I discussed, let me read those points out. In chapter 12, we shall read about the Bohr model of hydrogen atom. You would have already learned it in your atomic structure in chemistry. Okay. So you would have heard about the Niels Bohr's atomic model, which was proposed in 1911, that the electrons are going to revolve around the nucleus in a circular orbit. Right. So having all those points in mind, let me take certain considerations and you guys think and tell me. Okay. Don't be in a hurry to answer. Think and tell me. If I take this to be the atom, then the atom comprises of a central part called as the nucleus, and the electrons are going to revolve around them in a circular orbit. Let's say the radius of this particular orbit is r. Okay. And let's say the tangential velocity the electrons have is v. Okay. Now tell me, guys, I need to calculate the amount of current that this electron is going to contribute. So how do I calculate the current? So I'm going to derive what is the topic we are going to see? We are going to derive the magnetic dipole moment of how many electrons? Of one revolving electron. So our concentration is going to be only on the current produced due to one electron. We are not concerned about other parameters. Let's see how to do it. Can you guys tell me? So when somebody asks you what current means, so what is current? Basically, it is the rate of flow of charge. So the amount of charge E that is flowing for one time period, can I call it? So when the electron completes one revolution, I can say that there is a current constituted due to the motion of that electron. Does that make sense? right? So I is equal to E by D. I didn't put a negative sign here because we obviously know that electron is negatively charged. So we need not put the negative sign. And we also know the fact that when electron is revolving in anti-clockwise direction, current is going to be in the, right, it's a simple question.
Clockwise direction.
Anti-clockwise.
Clockwise, right. When electron is revolving in anti-clockwise, current will be in the clockwise direction, correct? Oh, sorry. Current is going to be in the clockwise direction. So I is equal to E by D, guys. And remember, it is in the clockwise fashion. Now comes another question. I is equal to the charge of the electron. I'm not disturbing it. Divided by what is the time taken by the particle to complete one revolution? Is it not 2 pi r divided by v? Guys,
Yes.
2 pi r is the circumference divided by the speed with which it is revolving. So we will go to the numerator. So E into V divided by 2 pi r is going to be the amount of current that is going to get generated in the material. Okay. See, actually, I can stop the derivation with this. But generally, whenever, see, I'm going to give you another logic. Listen to this carefully. The main objective of deriving a formula is not to solve problems. Okay. The main objective is to ensure that you're able to do those things, replicate them practically, and see. If suppose I want to calculate the current due to this electron, the most difficult thing that I'll find is how to find the velocity of electron. It is not possible. And I cannot find the radius of the orbit every time. I cannot find the radius of every orbit every time, and then I cannot do it. So I need to convert everything into a general parameter so that things become easy for us. Okay. So how can we do that is the question. Okay. Am I clear till this step? I will show you. So I is equal to E by T and T is equal to 2 pi r divided by V. So what did you get the value of current as? EV divided by 2 pi r. Okay. But what is the topic again? We need to derive the magnetic dipole moment. The reason why we are talking about magnetic dipole moment is I'm more concerned to know which side is going to be like a north pole and which side of the atom is going to be like a south pole. And how much is going to be the value of magnetic dipole moment it is going to exhibit so that it is able to attract or repel the other particles. Okay. So for that, what I'm going to do is concentrate. If I take the magnetic dipole moment as capital M, from our previous chapter, what is the formula for magnetic dipole moment? It is the current multiplied with area. If you guys remember, it is well and good. If not, make a note of this. Okay. The basic formula for magnetic dipole moment is actually N into I into A. Okay. It is N into I into A, where N is the number of turns in the coil. But here, since there is only one loop, I didn't take that N. I took that N as 1. So M will be equal to I into A. But what is the value of I, guys? Is it not EV divided by 2 pi r into what is the area? It is pi r square. So R and R are gone, pi and pi is gone. So I will have EVR divided by 2. Again, I will face the same issue. I cannot use this formula as a dipole moment because practically it is difficult for me to calculate V and R. So what I will do is, I will I will multiply and divide with a particular parameter that is nothing but the mass. So if I multiply with the mass of the electron and divide it with the mass of the electron, E into V into R divided by 2. Okay. Now look at the rearrangement I'm going to do. E divided by 2 times ME into ME into V into R. Okay. This is step clear. If I'm not wrong, you would have seen this expression in your 11th standard somewhere. Angular momentum. Yes. So E divided by 2ME and angular momentum is represented. Angular momentum is represented by the symbol capital L, and this is capital M. Okay, so the magnetic dipole moment is equal to E divided by 2me into angular momentum. The reason why we brought everything in terms of angular momentum is because, can someone tell me what is the use of this angular momentum? Why are we unnecessarily bringing this into picture? Because there is an important quantization condition given by Niels Bohr with respect to the stability of an atom. One is out of this oneness, the electrons will be able to revolve only in those orbits where the angular momentum is dash. Have you heard this in atomic structure? I repeat it. So when you talk about the orbits, he told the electrons will be able to revolve only in those orbits where the angular momentum is quantized. Have you heard this? No? Only in those orbits where angular momentum is quantized. And the value of angular momentum is like this. He has given L is equal to N into H divided by 2 pi. Have you seen this expression? Where N is the orbit number, or you call it as principal quantum number. H stands for Planck's constant, and 2 pi is obviously a constant. Okay, so let me take this as 4. So using 3 and 4, what do I get? M will be equal to E divided by 2 times ME into NH divided by 2 pi. So what do I get? N into H into E divided by 4 pi into mass of an electron is going to be the value of the magnetic dipole moment. Guys, are you able to understand?
Yes.
So let me show you the steps. This is the thing, angular momentum. I'll explain the step item, not at come. I'll do that. Okay. So he has told that the angular momentum is quantized. Okay, that is NH by 2 pi. And UL is given as this value. Okay. So I've just given you a crisp version of it. For all other things, I explained it, right? So now you read textbook, you'll understand it better. Let me know once you're done.
Finish, sir.
Finished? That's good. Listen. Now, if I put n is equal to 1, okay, if I put n is equal to 1, then m will be equal to h into E divided by 4 pi into mass of electron. See, h is Planck's constant. I hope everybody knows the value of it. It is 6.626 into 10 power minus 34 joules per second. Okay. You have all those values in textbook, don't worry. E is the charge of electron. It is 1.6 into 10 power minus 19 coulomb. 4 pi is a constant. Mass of electron is 9.1 into 10 power minus 31 kilogram. Now listen to this carefully. Listen to this carefully. If I substitute all these values here, then you will get the minimum value of magnetic dipole moment. and that value comes out to be 9.27 into 10 power minus 24, and the unit of magnetic dipole moment is ampere meter square, because magnetic dipole moment is I into A. I is in ampere, meter area is in meter square, ampere meter square. Okay, so this value is what is called as the Bohr magneton. This value is called as the Bohr magneton. Is it clear? Any doubt till whatever we discussed now?
No, sir.
No, sir.
Good. So I hope everybody made a note of this. Now I have an important question. Remember, magnetic dipole moment is a vector quantity. Angular momentum is also a vector quantity. Now the question is, in a particular atom, how is the magnetic dipole moment going to be with respect to the direction of angular momentum? Okay, let's see. Okay, so I want you all to pay attention, 100% attention, because this is again another tricky concept. See, if I take this as a circular loop, magnetic dipole moment is exhibited only for loops. For conductors, open conductors, there is no concept of magnetic dipole moment, because formula is I into A, you need an area. Now, if I take this mobile phone, observe, let's say the current is flowing in the clockwise direction. So you are seeing something, right? Let's say the current is flowing in the clockwise direction. Okay. Then how to find the direction of magnetic dipole moment? Anybody? Let's see if you guys know it. Okay. I'll give you a hint. Let's go back to electrostatics. There is something called as electric dipole moment. Right. So what is the direction of electric dipole moment?
Negative to positive.
Negative to positive. Negative charge to the positive charge. So similarly, here which pole is similar to negative charge, and which pole is similar to positive charge?
North is similar to positive and south is similar to negative.
North is similar to positive charge, and
South is similar to negative.
Negative charge. Okay. If suppose the current that you are able to see is flowing in the clockwise direction, I gave you clock rule. When current is flowing in the clockwise direction, which pole are you facing?
South pole.
Very good. So you are facing, see, suppose I take my hand and I say that the current is flowing in the clockwise direction, you are facing the south pole. So when you see from the back side, it is going to be north pole. So what is the direction of magnetic dipole moment? It is similar to that of electric dipole moment. Electric dipole moment from negative to positive. Magnetic dipole moment will be from
Positive to negative.
no.
Negative to positive.
Here there is no negative positive. I asked which pole is similar to negative pole.
So from
It will be
south
from
to north.
Purida, I'm just trying to
South.
create. Yes. So whenever you study about electric field, it's a similar thing will appear here also. Electric dipole moment is from negative to positive charge. Magnetic dipole moment is from south pole to north pole, because the negative polarity is similar to south pole. So when you see the current going in the clockwise direction, you're able to see south pole. So the magnetic dipole moment will be into the plane, into my palm. If suppose the current is flowing in the anti-clockwise direction, then the direction of magnetic dipole moment will be away from the palm. See, every time you need not sit and do this. So what you can do is, you can take your right hand. Okay, listen to this very carefully again. There is right hand thumb rule, right? Right hand thumb rule, where do we use it? We use it to find the direction of magnetic field due to a current carrying conductor. What do? We extend the thumb of our right hand in the direction of current and curl the fingers so that you get the direction of magnetic field. Now what you do is, for finding the magnetic dipole moment, you use the same right hand thumb rule in reverse order. What do I mean by reverse order is, to find the direction of magnetic field, first you will extend the thumb and then curl the fingers. Now you do the reverse. Current is flowing in clockwise direction, right? Take your right hand, just blindly curl the fingers in the direction of current and extend the thumb. That will give you the direction of magnetic dipole moment. Please make a note of this point. So how you find the direction of magnetic dipole moment using right hand thumb rule? Curl the fingers of your right hand in the direction of current and then extend the thumb. Right? Did you all note it down?
Yes.
No.
Yes, sir.
What is the direction of angular momentum? Angular momentum is r vector cross p vector. Okay. So if this is the circle I'm trying to see, I'll show you. This bottle is there. No? If this is the circle I'm trying to talk about, the electron is revolving in the anti-clockwise direction. So the velocity of the electron here is upwards, tangentially upwards, and radial vector is in this direction. So r vector cross p vector will give you the answer. So when you apply the right hand thumb rule, you take your right hand, take the hand in the direction of first vector and curl your fingers towards the second vector and extend the thumb. So what is that you're able to understand? Angular momentum is towards you, whereas the current is in clockwise direction. Recollect it. You only told current is in the clockwise direction. So when you curl the fingers in the clockwise direction for magnetic dipole moment, it is into the plane. So what is the important conclusion that we can draw in this case? When an electron is revolving in anti-clockwise, it can be in any direction. When an electron is revolving and you're talking about the angular momentum, the magnetic dipole moment and the angular momentum are always in the opposite directions. Okay. Since they are always in the opposite directions, what is going to happen is, if I write m as a vector quantity, then m vector will be equal to E divided by 2md into minus L vector.
Sir, are you writing on the screen?
Yeah, I'm sharing my screen also.
For me,
I can't see.
Sir, we are not able to see.
So if I give a vector notation, now I hope you will be able to see. So for the same expression, if I convert it into the vector form, then m vector will be equal to E divided by 2 times ma into minus L vector. Means the magnetic dipole moment and the angular momentum of the electron are always in the opposite directions. Please make an important note, because they have given it here. This can be a 1 mark question if I have to talk in exam perspective. Where is it? You're able to see this thing. There is a minus sign here. So whenever they write it in vector form in textbook, they will write it in bolds like this. Since every time in the notes we cannot put this bold, we are using a vector symbol on top of it. So if it is written without bold, it is a scalar form. With bold, it is vector form. So is it clear, guys? Is it
yes.
clear?
Yes, sir.
So I've taken this thing. Okay. So due to this, and this is the reason why every material in this world, since it is made up of atoms, and the atoms are made up of electrons, and electrons are in revolution, this is the main reason why every material has an inbuilt property in it to exhibit the property of magnetism. Okay, this is the first and the foremost important point that you need to know to start this chapter. Okay, so till now, whatever I discussed is the magnetic dipole moment in terms of current. I just want to give you one last point before we wind up. That is a magnetic dipole moment with respect to a permanent magnet. So if I take a permanent magnet, then it has a north pole and a south pole, right? So if I take the distance between the north and the south pole as 12, so the reason why I'm taking it as 12 is the same scenario as that we have seen in electric dipole. There we would have taken it as 2a, right? Same logic. 12, okay? Then each pole has a property called as pole strength associated with it. So, because each pole will have a strength associated with it, the extent to which it is able to exhibit magnetism is what we call it as pole strength. The pole strength multiplied with the distance of separation between the two poles is what we call it as magnetic dipole moment. So we know what is electric dipole moment, Q into 2a, right? So when you talk about charge, you speak about Q. Whereas when you talk about magnet, you speak about pole strength. So pole strength multiplied with the distance of separation between them is what we call it as magnetic dipole moment for a permanent magnet. Okay. So I would like to give you some time to absorb this concept. In the next class, we will be discussing about the Coulomb's law of magnetism, and we will see these derivations. Okay. Then we will see how a solenoid, what we have learned in the previous chapter, is able to behave like an equivalent bar magnet. This is also an important derivation. You will get for 3 marks in the exam. Okay, I'll explain all these things, but before that, you guys should ensure that you revise and come. Okay, or else it is going to be tough. Apart from that, any other doubt from today's class, guys?
No, sir.
No, sir.
That's good. So I'll see you all in the next class on Monday. Okay.
Thank you, sir.
So
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.